Hi, I'm Micah Chrisman. I'll be recording the first 10 slides of my talk at the Quantum Topology Seminar that was deleted due to a technological malfunction. So here we go. I'll be recording from the beginning, out of order, while wearing a New Order t-shirt. Okay, so today we're going to talk about why the virtual knot concordance group is not abelian. So before we begin, just give you a few references. So most of the talk will be from this paper, Milner's Concordance Invariance for Knots on Surfaces. We'll also talk a little bit about the paper Concordances to Hyperbolic Prime Virtual Knots and the paper Virtual Concordance and the Generalized Alexander Polynomial with Hans Boden. While we're going through the talk, we'll talk a little bit about some older papers with both Hans Boden and Robin Gaudreau. There's a lot of calculations in those papers which inspired the results in the more recent papers. Okay, so let's talk a little bit about the motivation behind the virtual knot concordance group. So what does it mean for two classical knots to be concordant? So two knots K and K star in the three sphere are said to be concordant if you take a copy of one of them, say K in S3 times 0, and then a copy of the other one, say K star in S3 times 1, and there's an annulus, properly embedded annulus, between the two of them in S3 times 0, 1. So you can do this either in the smooth or topological setting. Here we'll just talk about the smooth case for the most part. Recall that the concordance classes of classical knots are a group, and in fact they are an abelian group. Lots is known about the concordance group of classical knots in both the smooth and topological settings. So for example, there's the Cott filtration. So Cott here stands for Cochrane, Ore, and Teichner. And so this filtration, organizes sort of all of the famous invariants that we have for classical knot concordance in the topological category. So you have this filtration F0, F.5, F1, and so on and so forth. And as you go deeper into the filtration, you see more and more information about the classical knot concordance group. So at F0, you see the knots where the ARF invariant vanishes. F1, you see the knots which are algebraically sliced. And so those are the knots which have a Seifert matrix which has a block of half-dimensional block of zeros in it. And then as you keep going down to F2, you see the knots which have vanishing Casson-Gordon invariants, and then so on and so forth. Okay, so I mentioned this particular bit of information about the classical knot concordance group to point out that these invariants, the ARF invariant, the algebraic concordance group, and the Casson-Gordon invariants, they're defined ultimately using the Seifert form. And to use the Seifert form, of course, you have to have Seifert surfaces, which the knots bound. And so in particular, that means that the knots that you're talking about have to be homologically trivial in the three sphere. Now, of course, all knots are homologically trivial in the three sphere. But that won't be the case in the setting that we care about. So what do I actually care about, at least today, anyway? So we're going to talk about a definition due to Turayev for concordant knots and thickened surfaces. So here we'll have surfaces sigma and sigma star, which are closed and oriented. And we'll have two knots in the thickened surfaces, K is in sigma times I, and K star is in sigma star times I, where I is 0, 1. And we say they're virtually concordant if there's a 3-manifold W whose boundary is the union of the two surfaces. And there's a properly embedded annulus lambda whose boundary is the two knots, K star and K with its orientation reversed. Okay, so a couple things to point out about this definition of Turayev. Okay, so first of all, if you have two knots and thickened surfaces, they may not necessarily be homologically trivial, in H1 of the thickened surface. So the invariants that we talked about before don't immediately extend to this setting. So we're going to need something new. Just as a definition, we'll say that a knot is slice if it's concordant to the unknot in the thickened two-sphere. An important thing to point out is you can be slice and not be homologically trivial. So there's many examples of that case. Okay, now great observation of Kaufman is that you can use virtual knot diagrams to talk about this concordance defined by Turayev. So just as a bit of a review, here we have a virtual knot diagram. Here, this is a virtual crossing. Here you have a classical crossing. And for every one of these virtual knot diagrams, you can draw them as a knot on a thickened surface as follows. So at each crossing, you draw a little disc, which we think of as a 0 handle. And along each arc of the diagram, you put a little 1 handle. And so that gives you a compact surface. So it's pictured in the middle here. And that compact surface has some boundary components, which you then close by adding 2 handles to it. And then you get a nice knot diagram on a surface, which you can then think of as a knot in the thickened surface. Okay, so let me just remind you of the extended Reidemeister move. So we take these virtual knot diagrams. We have these moves that we define upon them. So we have the first row here is the usual Reidemeister moves. And then the second row, together with this one off to the side, tells you how the virtual crossings interact, and then also how the virtual crossings interact with the classical crossings. All right, so to get virtual concordance, as in the definition of Turayev, we need to add some additional moves. So we have saddles, and we also have births and deaths. So you want to think of these, just as this annulus that goes between the two knots. If you have a Morse function in this thickened 3-manifold, then these tell you what happens as you pass through different types of critical points. So, births and deaths, it correspond to local maxes and local mins, and saddle points correspond to saddles, just like you have in calculus, right? Okay, so what is virtual knot concordance then? Is you just take these virtual knot diagrams and you mod out by the extended Reidemeister moves plus births, deaths, and saddles, such that the Euler characteristic is equal to 0. So number of births minus number of saddles plus the number of deaths is equal to 0. So that last condition there, just to guarantee that you really do have an annulus that goes between the two knots. You do have to also require that the sequence is connected in the sense that there's no closed components in your concordance. In practice, you can keep track of this, by drawing, say, the Reeb graph of the movie. All right, so an interesting thing to point out is that the two definitions that I've just given you are equivalent. So this virtual concordance of knots and thickened surfaces, which is due to derive, is equivalent to the definition of virtual knot concordance given by Kaufman, and they're the same based on theorem of Carter, Kamada, and Saito. Okay, so here's just a little movie here indicating a virtual knot concordance. So this is 5-12-16 from Green's table. This is not the diagram of 5-12-16 from Green's table. There is an isotopy that's needed to put it into this form so that it has a short concordance movie to the unknot. So we start there on the left-hand side, and the little blue arc here corresponds to where we're going to perform the saddle. And so after you perform the saddle, you get a 2-component virtual link. And after doing some extended Reidemeister moves, you can separate these into a 2-component unlink. And so if you kill the red component, you had 1 saddle and you had 1 death. And so that means, if you keep track of what you're doing, that you have a concordance to the unknot because the Euler characteristic is equal to 0. And so therefore, sure enough, we have a concordance between the knot 5-12-16 and the unknot. And so we would then say that 5-12-16 is slice. Okay, so a few things are known at this point about virtual knot concordance. So the first thing one should always mention about this is that 2 classical knots in the 3-sphere are concordant in the usual sense if and only if they are virtually concordant. So this is an important theorem of Bowden and Nagel. For classical knots, you can specify what the generators of the knot concordance group are. And so you can show that every classical knot is concordant to a hyperbolic knot and also concordant to a prime satellite knot. So those are theorems of Livingston and Kirby and Licorice. And then also it's true that you can fix such generating sets so that the Alexander polynomial is preserved. So by that I mean, if you pick a concordance, a representative of the concordance class, you can find another one which is prime and has the same Alexander polynomial. And so that's a theorem of Bleiler and Nakanishi. Okay, so this is also true in the virtual knot setting, although it's quite a bit difficult to show that knots are prime in this setting. So by prime, I mean here prime in the sense of Matveyev. And so that just means that, not only is the knot locally trivial and thickened surface, but it also cannot be decomposed into 2 virtual knots, or composed of 2 knots of thickened surface. We're also allowing for a decomposition of the ambient space. So those are some very nice papers by Matveyev. I recommend you take a look at those if you're not familiar with that idea. But it's quite a bit more difficult to show that a virtual knot is prime, because it's not just the case that it's locally trivial, as in the case of knots in the 3-sphere. You also have to show it can't be decomposed into pieces where you have one knot in one genus surface and then another knot in another genus surface, and together they add together to give you the actual knot. Okay, but in any event, it's still true that every virtual knot is concordant to a prime satellite knot, a prime hyperbolic virtual knot, and also a if the knot is almost classical, a prime satellite almost classical knot and a prime hyperbolic satellite knot, prime hyperbolic almost classical knot, I mean to say, having the same Alexander polynomial. Okay, so that's just something to point out. about how those concordance classes behave. Now, to get a group structure for virtual concordance, you have to look at the case of long virtual knots. So here I've drawn two long virtual knot diagrams, 2.1 and 3.1. Definition should be clear. What I mean by a long virtual knot, it just means that you have, you're just tying a little knot in the real line, and you allow both classical and virtual crossings. And the group operation is just concatenation. If you look only under equivalence, this is generally not going to be a group because you don't have inverses in the same case that you have for classical knots. But if you consider them up to a concordance, you do get a group structure where the operation is concatenation and the identity element is just the long unknot. So just think of that as, say the x-axis or something. So in 2008, Turayev observed that you have, a group structure on these things, but it wasn't clear whether or not it was actually abelian in the first place. So he asked at the end of his paper, it's the last sentence in his paper, cobordisms of knots on surfaces, is it abelian? Okay, so we'll hope to answer this question today using some new techniques. Okay, so in addition to the theorems I mentioned before about sort of the behavior of concordance classes of virtual knots, there's quite a few virtual slice obstructions which are now known. So in the paper I just mentioned by Turayev, he introduces this amazing invariant called the graded genus. It's an absolutely excellent slice obstruction, and it also gives very good bounds on the slice genus. A little bit later, Dye, Kestner, and Kaufman extended the Rasmussen invariant to virtual links. And there's a second Rasmussen invariant due a bit later to Will Rushworth. And then one thing that's sort of interesting about virtual knot concordance is, after this idea was popularized by Kaufman and others, it turned out that some invariants that people knew and loved, people have known and loved for a long time, are also just invariants of virtual knot concordance. So one example is the odd Rythe. Another example is the affine index polynomial or the Rythe polynomial. Those are equivalent. Another example is the Henrich-Turayev polynomial. I didn't put that on the list, but that's another example of something that has been around for a while, but wasn't known to be a concordance invariant until much more recently. For almost classical knots, there's these things called directed signature functions. And I don't think I mentioned this before, so let me go ahead and do this now. What does almost classical mean? Almost classical means that it has a homologically trivial representative in some thickened surface. Okay. And so this is a special class of virtual knots. Because they're homologically trivial, they bound Seifert surfaces, and you get interesting obstructions coming from the Seifert form of those. They also provide bounds on the slice genus. In fact, they're very good bounds on the slice genus. So, up to 6 crossings, the slice status, at least whether or not any almost classical knot is slice, is completely determined already using the graded genus together with the directed signature functions. Okay, another somewhat different type of slice obstruction are these things called coverings of knots or equivalently parity projection. So those are functorial under concordance. And so, you can use that to beef up different kinds of concordance invariants if you know how to use them. So that's kind of useful. And then lastly, we have the generalized Alexander polynomial. So one thing that's useful to point out is that the generalized Alexander polynomial dominates both the odd-Rive and the affine index polynomial. And it also dominates the Henrich-Derive polynomial. And that's a theorem of Blake-Malor, who showed that you can get the Rive polynomial and the odd-Rive from the generalized Alexander polynomial, essentially by a specialization and a factorization followed by a specialization. So the invariants that we'll be talking about today are a further generalization of the generalized Alexander polynomial. I should also point out that the generalized Alexander polynomial goes by lots of different names. So one very common name is the Sawalik polynomial. It was originally discovered by Jager, Kaufman, and Soler using some techniques from statistical mechanics. And then it was later, given a combinatorial description by Sawalik. And there's lots of equivalent versions that appear in the literature. So there's one due to Silver and Williams, which is very useful. They call it the generalized Alexander polynomial. So, that's why I'm using that terminology there, because it's, more accurately describes what it actually is. Then there's other versions. There's one due to Manturov, and there's also one due to Bowden, Gaudreau, Harper, Nikas, and White, and that'll actually be the one that will give us our deeper invariants. The group that they use to define that. It will also be the group that we use to define our invariants. Okay, so I believe that is where the second part of the talk that was recorded first will pick up. So I'll just stop there. And thank you so much for listening to the first part of the talk. And also I'd like to thank the organizers for giving me another opportunity to just give a little talk about this. So I appreciate it so much. Thank you for listening.